series on STEM education for this semester. We usually get 4 talks a semester. And this series is offered through the Barnard Noyes Scholars Program funded by NSF. The Barnard Noyes Scholars Program is a program run by the Barnard Education Program with the intention of preparing teachers in STEM fields for K-12 education. Tonight it is my pleasure of introducing one of my colleagues, Barnard Professor of Mathematics, David Bayer. Professor Bayer received his undergraduate degree at Swarthmore, which he just told us a little bit about, and his PhD at Harvard University.
I got out again, just barely that time.
Oh, you got out. And Professor Bayer's many accomplishments actually include some really interesting things that we don't necessarily think of as mathematicians doing, but one was serving as a consultant for the film A Beautiful Mind, 2001 film about Nobel laureate John Forbes Nash Jr., and he also had a small role in the film as one of the Penn Ceremony professors.
Congratulations. I got 20,000 residuals for that over the years. It's crazy. Just imagine if you had a real part.
Oh my God. It's pretty cool.
Yeah.
He also co-authored Macaulay, a computer algebra system for computations in algebraic geometry and commutative algebra, which maybe you'll tell us a little bit about. I don't know.
That word algebra, I think it sounds familiar. Yeah.
Okay. And Professor Bayer, along with several colleagues, holds a U.S. patent for a method and apparatus for optimizing system operational parameters.
Linear programming.
We are lucky to have him here at Barnard. He's been here since 1987. He's currently the chair of the mathematics department.
Anyone want to be chair?
And his specialties include linear algebra, modern algebra, and combinatorics. Tonight, he's here to talk to us about patterns, the language of patterns.
Yes, right.
And help us muddle through some interesting possible K-12 education
Yes.
thoughts. So let's give Professor Bayer a warm welcome.
Thank you. Okay, so some of you who studied computer science will have encountered some of this in the computer science curriculum. It's very basic idea about how you model patterns using algebra that I think is a core part of math. And as a core part of math, I like the idea that you're thinking about how it could be actually introduced in K-12. I mean, one thing that I'm keenly aware of as I teach linear algebra and then, say, ride the subway and see some 2-year-old reaching over to their parents' magazine and trying to do the pinch move on the magazine to get the screen to change, and it's not changing. That if you're growing up for your entire life with that as your visual experience, then most of what we do with notation is shaped by the fact in the 19th century they had typewriters with a layout designed to slow you down, and all of mathematics was what you could get on a page using one of these typewriters. And so it's kind of like it blinds us to what is the most powerful part of our brain is our visual part of our brain. And so what I like about the ideas I'm going to show you is that you can teach some of it with drawings and thus see it more immediately than if it was other kinds of notation. And even when linear algebra comes in, linear algebra is one of those subjects that you normally only see in college. But linear matrices, when they're introduced as compositions of linear maps, it sounds rather abstract. But there's a way in which matrices are the natural way to model what I'm talking about here. And I think that one could introduce matrices much earlier in the K-12 math curriculum if you acted with a straight face, like this was the natural way that one thinks about matrices, and then learn the other approach later in college. So the idea, I mean, what does it mean to be rational? And of course, this is a loaded word. I don't mean as opposed to emotional. I mean, the idea of rational numbers, is that we have a fraction 2 over 5, we have a fraction 4 over 10, but within, there we are, commutative algebra. Commutative algebra is the part of algebra where order doesn't matter, that you can just as easily study, an expression where you take 2 polynomials and you divide one polynomial into the other, and this is considered a rational expression, just as these are considered rational expressions. And when you take modern algebra, you study a pattern of which these are two special cases. But these are both in the commutative realm where order does not matter. In the real world, order matters. I mean, in linear algebra, you can't multiply matrices either way because order matters. But an experience that one might not think of as being the same as this is many text editors are useful not only for writing prose, but also for writing computer programs. And the ones that are used for writing computer programs have features that allow you to search for patterns in the text. And most people who just use them for prose may be unaware of these features, but they're worth learning a little bit of at a time, no matter what you do, because it's an incredibly powerful search function to, instead of saying find anything that has this 3 letters as a subword, you could more directly just say find the following. So if I have, just to keep this nice and simple, if I had letters A and B, then this is an expression that is something you could type into what's called a regular expression search engine. And it has a very concrete meaning, but before I have a concrete meaning, what I want to say to you is that this somehow you should think of as being the same idea as this, except that over here, order matters, and over here, order does not matter. And one thing that you take absolutely for granted when you think of a rational expression is that the main feature of a rational expression is it's got this bar showing where the division took place, and everything above the bar is the numerator, everything below the bar is the denominator. And the whole idea of being able to shepherd the sheep into two herds like this is the idea that order doesn't matter. So you can just tell everybody to go above the bar or below the bar, that you get this advantage of writing things in the commutative case. So you shouldn't expect a rational expression to be this easily spotted as having a bar to divide by in the order matters case, because order matters. But let me tell you what this expression means. This star pattern means 0 or more times. In other words, this is a shorthand for search for any of the following strings in the text you're looking at. And so 0 times would be A, leave this out, B. 1 time would be A, put this in once, and then do B. 2 times would be A, put this in twice, and then do B, and so forth. And then to take a slightly more complicated pattern, we could do A, B, bar, C, star, B. And the meaning of this symbol, this kind of plays the role in computer logic that a plus sign plays in the ordinary case. A lot of this is translating languages because it stands for or. So the idea that what this literally reads as saying is you do A and then you do any number of times 0 or more, choose something from this menu. Either do an AB and then consider what your next move is, or do a C and then consider what your next move is. So if we were to actually list what these look like, you could do A and then do nothing, and then B. So that's the same as this one. But now there's 2 cases. If we're going to do once inside the parentheses, we could do A, and then AB, and then B to end over here. Or we could do A, C, B. I'm stacking up the 2 choices that use it once. And then if we're going to use it twice, then it's A, and then we could do AB, do AB both times, and then B. Or A, do AB the first time, and C the second time. Or do A, C the first time, and AB the second time. Or do A and do C both times. And keeps going. And this is an infinite set. I just listed, so again, since there's a 2-way choice, if you do 3 of these, that's 2 times 2 times 2 is 8. I mean, so you can see this goes 1, 2, 4. The next list will be 8 long. This is an infinite list. These are the patterns that are the bread and butter of computer programs in computer science. The idea being that when you write a computer program, you're developing an artificial language to talk to the computer in, as opposed to natural languages where people are more organic. And so our language defies as perfect a classification as computer languages. Computer languages are deliberately made crisp and perfect. So if you use something like Python or any, a lot of students use, or R if you're in statistics, if you've used any language whatsoever, there are parts of the language that are too complicated to capture with rational expressions. And there are other parts of the language that are so straightforward that they can be captured by rational expressions. But these are like the viruses of all life forms. These are the one-celled organisms of all life forms, is the things that you can capture with expressions like this. And what I want to give you a feeling for is what this actually really means. So first of all, what goes wrong in a program? You can't figure out balanced parentheses by a notation like this. In other words, if you're trying to search for an occurrence of unbalanced parentheses in your computer program, this is not going to find it. And the reason is that this is such a fundamental concept is that there's a hierarchy of different languages in computer science. Noam Chomsky, who worked in both natural language and artificial language, is actually responsible for a lot of the introduction of this hierarchy. But the way the hierarchy works is you imagine that you have a limited memory. And so you ask, what can you correctly identify with a limited memory? And the difference between these two examples and the example of balanced parentheses is the way I learned a long time ago to balance parentheses. I just start counting. I make a hill. I mean, if I start in deep 0, then open parentheses. Now, after I see this, I'm in deep 1, then I'm in depth 2, then I'm in depth 3. This closes me back to depth 2. This closes me back to depth 1. This takes me out to depth 2. This takes me back to depth 1. This closes me back to depth 0. So the way in which I would automatically figure out that this was a balanced set of parentheses without having a weird open parentheses that wasn't matched is that, first of all, the depth never goes negative. This would not be allowed because where's the start? And second of all, I end up in depth 0. But the sense in which this requires infinite memory is that if I'm considering all possible strings of balanced parentheses, there are some out there that are 50,000 deep. And so unless I can accurately count to 50,000 and get back out again, I can't tell. And so there are other parts of computer programs where you do if, then, else. But you're allowed to have nested structures. Like inside this then clause, you might have an if-then clause. And inside that, you could have an if-then clause. This is the same idea as nested parentheses. So an arbitrary computer program corresponds to what in algebra people call an algebraic expression, not a rational expression. So in other words, if you think about the hierarchy of numbers, integers are the simplest numbers, fractions are the most basic things built from them. And then like square roots, like square root of 2, are the next simplest kinds of numbers. And then the really hard numbers are like pi, e, the numbers you study in calculus that you can only understand using power series that don't actually have simple formulas defining them. In some sense, recognizing a balanced parentheses is like the square root of 2. I mean, you write out a decimal expansion of a square root of 2, it just keeps going. You can't predict it from seeing part of it. I mean, you can by knowing what square root of 2 means, but there's no easier way of doing it. Whereas what's going on in the patterns I'm talking about, these are called regular expressions, is one name for this. And the machines that recognize regular expressions are called finite automata. So finite automata is that there are many ways of saying this, but basically one only needs a finite memory to remember enough to tell whether you're good or not in these cases. And so the easiest way to show you that is to draw the pictures that go with this. So there's a picture for the first case. So I'm going to call my first square x, my next square y, my next square z, and my next square w. And I'm going to label this as my start. And I'm going to label this as my good, or let's call it accept. So give positive affirmation if you ever reach that square. Then I can make a board game, so that looking at these strings, I'm simply playing this board game. And so the idea is that from the start, there's only one thing that I can legally see first in a pattern like this, which is A. And so I write an arrow from X to Y with an A on it. And the idea is that if you're playing this game and the first letter you hold is B, not A, then you're here. You're out of luck. You just keel over and it's all over. But if you're alive still because you have an A, then after you play your A, you end up here on the game instead. So then how do we understand 0 or more times of A than B is we make a little side trip. A goes here, B goes here. And so you can see that the effect of doing A and then B is as if you did nothing, as you end up right back here. And so you can go in circles as many times as you want on this part of the game. And when you decide you're done, you have a final move, which is that a final B takes you to the end conclusion. Okay, so this is the finite state machine that goes with this regular expression. And this is only a slightly more complicated regular expression. Can anyone see how I'd fix that drawing to make it work for this one instead? Yeah, how would you do it? Yes, you have a loop from Y to itself, which is C. Right. So the sense in which I mean that your memory is finite is that you could be in the middle of reading one of these words and get clunked on the head and forget what you read so far. You don't need to remember what you read so far. You just need to remember where you were when you stopped. And so the idea is that there's many ways of defining this, is that you can say lots of words are equivalent if they put you in the same place on this drawing when you carry them out. What does this have to do with matrices? And I'm not going to assume that everyone in this room even has seen a matrix. I know some of you are pretty good at matrices. Is that true that some people don't know matrices and some do? The yes is yes, I don't, yes, I do. I can explain a little matrix theory here. Anyway, here's the, okay, so the reason I want to introduce this is that there's probably what I consider the best result in mathematics that explains everything that's going on here, does it in a really cool way. Because it says that the best explanation of this pattern understands what's going on here, where instead of using numbers, we use true and false. And the idea is true and false is sometimes called Boolean logic, but that you can do arithmetic with truth tables the same way you can do arithmetic with integers, except that your operations, instead of being plus and times, you do or and and. And so, what's conventional in computer science is to have 0 stand for false and 1 stand for true. So let me just make that clear once, false, true. And so if I have these operations, then the only way in which the first argument and the second argument be true is if they're both true. So you get this multiplication table for and. And then over here, or is true if either one is true, which means that this is true because the row, this is true, and this is true because this is true, and this is true because they're both true. So this table doesn't quite look like any arithmetic table that you would understand in ordinary arithmetic, but it nevertheless is the kind of Boolean logic which corresponds to computer science understanding of these drawings. So from this point of view, what does a matrix do in this setting? I mean, how would I present matrices to high school students without referring to linear maps and real numbers and calculus? is I would look at it instead as kind of a counting problem situation. So supposing we have x, y, z, and I have a path that goes from x to itself, and a path that goes from x to y, and a path, and I have this drawing for these paths. And I ask the following question: how many paths of length 6 from x to itself? I mean, this would be an interesting problem that refers to integers, not Boolean logic. But the transition to Boolean logic is pretty straightforward. So what we do is we do the following, is we make a table which tells us what one step looks like. And let's do x, y, z, and this is the before, or the start. And this is x, y, z after. I think I'll label it. It doesn't matter how you label it, but let's call these headings the before headings and these columns the after headings. And if we just make a table counting how many paths of length 1 there are from xyz to xyz, then what we see is that there's a path that takes x to itself. There's a path that takes x to y. There's no way to get from x to z because the arrows have directions on them. And then there's a path that goes from y to z. And there's a path that goes from z to x. And the interesting thing about this is that these can be multiplied just as numbers can be multiplied. So if this is one step times one step, then what I'd like to do to combine these is to combine these as 2 steps. I won't actually do the calculation out to 8 steps, although we could. And there's a basic building block that we need to understand to do this. So this is x, y, z again. Is we could, if we picture this going in this direction, let's say that we start at x, and this is at the beginning of time. So at time 0, we're here. And then at time 1, we could be at x, we could be at y, we could be at z. And at time 2, we could be at x, we could be at y. Well, we only care about x. We're looking at we want to find from x to itself. So the idea here would be that, what's the picture? I'm unfolding this. There is a move from x to x, and there's a move from x to y. There's no move from x to z. And then from x to x, there's a move, but there's no move from y to x, and there is a move from z to x. And so if you look at this pattern and say, getting from here to here, if this is the maze I have to go through, how can I get through this maze? Well, you can see visually the only way you can get through the maze is to go x, 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 which makes sense back in the original idea, is that in 2 steps, we don't have enough room to go around the world. The only hope of getting from x to x in 2 steps is to stay put and do the self-loop twice. But the way this gets written out in terms of numbers, if you have 1s and 0s for how many paths there are, is that you can add up the total paths by adding up the paths through here, plus the paths through here, plus the paths through here. And you end up with, there's one path into here, one path into here, no paths into here, one path into here, no paths from here, one path from here. And so really, literally, you're doing 1 times 1 plus 0 times 1 plus 1 times 0, which in higher math, you end up calling that the dot product. 1, 0, 1, dot, 1, 1, 0 is just float these till they're next to each other and then multiply them 1, 0, 0, and then add them up and get 1. So this table gets filled in from this table. Just thinking of what it means in terms of the steps works itself out as you can fill out this table by the same rule that people use for matrices in linear algebra for doing compositions of linear functions. So I don't want to go into too much detail about this, but I want to make a distinction between true, false. There's two questions you could ask. You could ask, is there a path? And how many paths? And so when I did path, when I introduced a little bit about path counting over there, I was talking about the question of how many paths. And the answer could be 0, 1, 2, 3, 4, blah, blah, blah. Whereas the answer for is there a path is you could say 0, no, there's no path, or 1, yes, there's one or more paths. So in some sense, the transition from integer counting to Boolean logic is simply one of collapsing all positive numbers into yes, it's a positive number. And so one way of looking at this multiplication table and these tables here is instead of thinking of this as or and, you could go back and think of this as plus after all and times after all. And then instead of being a 1, this is 1, 2, 3, 4, 5. These are all numbers like that. This is 1, 2, 3, 4, 5. Well, and then this is 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. And just notice how it works is that 0 plus 0 is 0, but 0 plus more than 0 is more than 0. More than 0 plus 0 is more than 0. More than 0 plus more than 0 is way more than 0. But the collapsing gives you this table. So there's this connection between Boolean logic, which is true false in computer science, and ordinary integers, which is what I learned when I was in K to 12 school. I never saw Boolean logic. I saw ordinary integers. So why do I say that here? Is that there's a way to there's a way to model a finite state machine in terms of matrices. And there's a basic theorem about them which says you can always do this. And so the idea, I want to look at this case here and just show you how this would work, is let's write down a matrix which corresponds to, this is going to be, now we're going to have 4 by 4 matrices. So I want to correspond a matrix that corresponds to A matrix that corresponds to B, and a matrix which corresponds to C. I'm going to make these 4 by 4. And so the general rule is going to be x, y, z, w. And then over here, x, y, z, w. And so I'm only going to write down those transitions in this drawing that have an A labeled on them, whereas here we didn't have labels. We just wrote down everything in one matrix. But here we do have labels, so I want to put everything in its own matrix. So the only places that I see A's over there is I see an A going from X to Y, so there's a 1 here. And I see an A going from Y to Z, so there's a 1 here. And the rest of it is just empty. And then where do I see B's? I see 2 B's. I see a B going from Y to W, and I see another B going back from Z to Y, right? And then I see, for C, I only see one place there's a C. I see 1 here. And so everything else I'm leaving blank is 0. And there are a total of 1, 2, 3, 4, 5 edges here, correct? And so I should see a total of 5 entries, 1, 2, 3, 4, 5. That looks good. So how do I tell whether the word, so one of the possible words in this path was ACB. Let's do something really simple. Let's do ACB, okay? Now, the first problem with what I've just set up here is that there are 2 conventions in math. And I don't know how you deal with this when you teach, but some stuff works left to right, like we read, and some stuff works right to left, like function composition in algebra. And a lot of people who use matrices in real-world applications like automata theory or probability theory reverse the meaning of the rows and columns in order to have the matrices work their way left to right like we read. But of course, not everyone reads that way. There are other cultures that read right to left or up to down. It's really just an arbitrary convention. But really, the path I'm thinking of is the path. I want to basically show that a path that starts with A and goes C and then goes B is accepted by this machine. And you can, of course, see by looking at it that this is the case. Is that here is the path which starts at the start, does an A, then does a C, and then does a B, and ends up at W, which is the accept state. So that is one of the words that we're supposed to accept with this machine. Only I want to draw this in this direction to be consistent with the convention used in linear algebra as taught at this university. So the idea is what you do is you put in a matrix. You put in the matrix for A, the matrix for B, and the matrix for C. And so I'm just going to sketch them in here. This is the matrix for A. This is the matrix for C. And this is the matrix for B. And you represent the fact that your start state is X out of XY, out of all of them. So you have an X here, and then you have zeros anywhere else. And you represent that the only good place to end up is W by writing a vector that says, yes, I like W, I don't like anything else. So this is the accept vector on this side. And so the interesting idea here is that the ordinary rules of matrix multiplication combine these matrices and these wing conditions exactly to model the game that we do directly by I when we say start at X and move around and end up at W, so we accept this word. So there's a theorem by this, it's actually back to the 60s, but it's still not completely appreciated, which is Schutzenberger. He asked two things about languages like this, is whether they are rational or not, and roughly it has to do with those expressions I showed you, and whether they're representable or not, which is exactly this idea. Can you come up with, in some dimension, a set of matrices that codify the language? And his theorem was that rational equals representable. And so that any time you're in a situation like this, you can come up with a matrix form. It's really just writing down this picture in matrix form. But basically, so this is the key to how computers identify patterns like this, is that in some sense they're doing something equivalent to carrying out this calculation. So I'm at the halfway point in this talk. The reason I wanted to set this up as a basic, this is the primordial language of patterns. This is the simplest kind of pattern because it requires finite amount of memory. What state are you, which of these four positions are you in is all you have to remember. Even if your word is 50,000 letters long and you're not sure whether it belongs or not, all you have to remember is what position you're in. But that there are many parallels throughout the STEM sciences for this pattern. This is just how it looks in computer science. The advantage to the way Schutzenberger stated this is he didn't care what number system you were in. So if you think he was talking about Boolean logic, then this just explains what people study in a course on automata theory and computer science in more words usually. And you know, at the level of drawings like this, you could easily teach K to 12. And I wish that you would, you know. But that you could easily switch gears to other algebras. And the most important thing you could switch to besides true-false is to switch departments over from the computer science department to the probability and statistics department. And you could talk about probabilities. And so the idea is that if you have, instead of, so really what we were saying when we said we want to consider the following words, we're basically assigning a function to all possible words. True if this is a word I like, and false if this is a word I don't like. And the way you would translate that to probability theory is instead of saying true versus false, you could ask, how likely is that word? And so one thing I would like to get at is, what is the actual meaning in probability theory of the analogy to this concept? So I don't want to really pursue the matrix approach. That's how Schuchenberry stated his work. But I want to just talk more directly by showing you a game. And eventually we can draw versions of this game, and which look just like that picture. But so the game is this, is that we're digging up craters in the moon looking for ores we can mine or something like that. And we dig up this box, and it's got a switch on the side, and it's got a light bulb. And they must have known it was us, because it's one of these, it kind of looks like a retro bulb. It's not LED, whatever. But so you turn the switch on, and you get a sequence of pulses out of this. I mean, that you turn the switch on, and then for a moment it shines green, and then for a moment it shines red, and then for a moment it shines red, and then for another moment it shines green. And you run it as long as you want, and it just keeps going forever. Or you can turn it off. And you turn it back on, and you want to see, well, the second time it turns on, does it do the same thing or not? And the second time you turn it on, yeah, it does green, and then it does green again, and then it does red again, and then it does red again. And so, oh, that's interesting. It's kind of random, isn't it? Well, actually, when people develop models for the stock market, it's not so different from this. I mean, actually, I'm really explaining is really one of the fundamental models that are used for trying to guess for a partially random process in the stock market. This is the language you could use for that. But let's say that you have a lot of grad students, and so you can have people in the lab doing this for a million years, writing down what happens. You build a robot to watch it and write down what happens. Then, the basic question that I'm leading up to is, I want to ask, what does it mean for this to be the equivalent to one of these finite processes? What does the finiteness condition look like? So there are various ways you could try to record your data. But I guess one way, let me draw you a possible model for this box. I mean, notice we can't pry it open to see what's inside. We're afraid we're going to break it. Let me show you what could be inside that's in this language, but describing probability theory instead of true-false theory. So now I have two states, x and y. That's it. And what I want to do is assume that if I'm at x, with probability 1/3, I stay at x, and emit red. Red is stop. I've stopped at x. Okay? And then over here, with probability 2/3, I stay at y, and let's just use again red for stopped. And then the complementary probabilities tell me what else happens. So here, the probability is 2/3 that instead of staying at x, I move to y, and the probability is 1/3 that instead of staying at y, I move to x. And maybe instead of using red and green, I should use red and yellow. Some people are red-green colorblind. Video cameras are red-green colorblind. They can't see this very well on camera, I know, from teaching my class. So we just saved it just in time. So yellow is proceed with caution. Okay, so we proceed with caution from x to y, and we proceed with caution from y to x. So notice that wherever you are, you could flip a die. A die is a singular for dice. And if it's 1 or 2, stay here. If it's 3, 4, 5, 6, go there. I mean, it's very easy to randomly move around from x to y, from y to x. And if this was what was inside the machine, so the machine basically started here. And so the first time you turn the machine on, it, with chance 1/3, goes from x to itself, and with chance 2/3 goes from x to y. And then if it gets to y, then notice the probabilities are reversed. Because now that it's at y, probability 2/3, it now stays to itself. and probably 1/3 it goes back to x. This is what's called a hidden Markov chain. I mean, it's the same idea. I could imagine making games out of this. It would be entirely suitable K-12, except that instead of being true-false, it's chasing colors like this. If this was what was going on inside the machine, but all we could observe was the following. All we could observe was when we turn the machine on, it starts at the beginning and then does one more sequence at random. So we get lots of individual trials. Well, here's how I would try to keep track of these trials. So my nomenclature here is red is always going to be a down and to the left, and yellow is always going to be a down and to the right. So in fact, I could, this is down and to the left, 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 this is down and to the right, down and to the right, down and to the right, down and to the right. And this is the start, and I'm at the start with probability 1. And so what does this model say? What this model says is that 1/3 of the time I'm going to stay still and go to, and stay at x. So 1/3 of the time and what I do is all you see is the light coming out. You see red light as I move through this curve, but you don't see y. That's what's hidden about hidden Markov chain is you don't have the actual model, you just have the observed phenomena that leads to the model. Okay, so, and then 2/3 of the time from 1, I go out to there. And so you can imagine there's various laws of large numbers in statistics that basically say that if you do 1 billion trials, you will see it shape up as 1/3, 2/3 with reasonable accuracy. Doing 100 trials, it's already going to be close, but you get more accuracy the more trials you run. So you could quickly develop this as your model. But now, this is a very simple problem, so it's easy to keep track. And we know that we started in position x. And then here, this means we stayed at x. Here, this means we moved over to y. You can't always do this labeling. I mean, in fact, I shouldn't be doing this labeling because I can't observe it. This tree is trying to draw what I can see from the outside of the box without looking inside the box. So really, I'm kind of sneaking that in as a teacher's aid for me to work out the numbers. But if we're still at x, and then what do the odds look like? Well, 1/3 of 1/3, which is a 9th, we end up here. Whereas 2/3 of 1/3, which is 2/9, we end up here. So we move like that. And then over here, the 2/3 puts me in the position y. And now 2/3 of 2/3, which is 4/9, I stay still at y. And 1/3 of 2/3, which is 2/9, I move over there. And so notice that my chart, it's 1 plus 2 is 3 plus 4 is 7 plus 2 is 9 over 9 is 1. That these 4 probabilities add up to 1. Every layer is going to add up to 1. I won't work out the next layer, but the idea is that if you ran billions of observations of this box, you would see a tree labeled like this that's telling you what happens. And so the question analogous to, I told you that balanced parentheses was not a finite problem. And this picture is a finite problem. So it turns out that this is a finite problem, and again, you can have a red matrix with a 1/3, 2/3 in it. I won't draw the matrix for you. And another yellow matrix with 1/3, 2/3 in it. I won't draw that for you either. But by using matrices, you could actually predict these probabilities. I mean, this is it from scratch, looking at this, how would you decide whether this was finite in the sense that there was a picture like this, in the sense that there was analogous to this picture here? Well, if there were only a short list of numbers, it'd be easy to just treat these as entries in a vector and basically plot these in n-dimensional space. Like right here, if I just had this information here, I could plot this in 1, 2, 3, 4, 5, 6, 7-dimensional space. Just by plotting it as the vector 1, comma 1/3, comma 2/3, comma 1/9, blah, blah, blah. So what you do when you have an infinite list like this, there is actually a notion of R infinity. It's an infinite dimensional space. And the idea is that if you took all the numbers going on forever, that you could think of that as being a point in this space. And then what does moving red one step look like? If I told you, no, don't look at this whole thing because you came in late. And what did you miss coming in late? Well, I turned it on, it was red once. That's what you missed. Right? Then what is your experience coming in late and having missed having turned on red once? Having turned on red once conditions the problem. Actually, in this particular example, it doesn't, because staying still is just like still being at the start. But in most problems, missing a turn conditions the problem. Well, the way in which you could picture that is you just ignore all this other stuff. You just basically, instead of having your point of view being here looking down, you take a red step, and your point of view is here looking down. Okay? And if you're here looking down, then you see an infinite tree, and you've got a rule for writing down a list of numbers to plot. You write down 1/3, 1/9, 2/9, whatever these numbers are. There's an infinite list. So you could plot that as a point here. And then if instead, say I ran a different trial of this thing, and the first thing was yellow, and we want to say, what does it look like after we've seen it flash yellow once? Then it's simply the question of what does this tree look like? You know, and we look at it, it's like 2/3, 4/3, 2/9. And so we could plot that. So what is the finite? So you keep going, and there's, you know, you get an infinite point cloud. I mean, this is what people in big data is all the thing these days. I mean, huge point clouds is what people worry about in statistics. This is more than huge. This is only in our imaginations. This is an infinite cloud of points living in an infinite dimensional space. And I'm asking, what about this would make it finite in the same sense that this is finite because there's only finitely many states? And what it turns out the answer is quite simple, is that in general, for an arbitrary set of numbers, if you did this, the cloud you saw would just be everywhere. It'd be an infinite dimensional cloud. Whereas if you walked into this infinite dimensional space, and you realize it's kind of a stretch of the imagination, we're going to just walk around in this infinite dimensional space and look at a point cloud. But if we walked in and looked, and this cloud was all in a plane, we'd go, wow, that cloud is all in a plane. So in some sense, the shifting from this point of view to this point of view is like a shifting in the plane. And so what people study in linear algebra is that when you have transformations of a plane, you can represent them by 2x2 matrices. So that, you know, it's finite dimensional matrices arise when you're looking at a finite dimensional situation. So, you know, in the automata case, you know, situations that repeated themselves exactly. You know, you would end up, if you ended up back at y, it's as if you were there the first time for what happens next. In this kind of game with probabilities involved, in general, I mean, again, this is a slightly strange problem because x is stable, it just keeps shrinking. But in general, when probabilities are involved, you'll never have the case that looking at all possible subtrees that there's only finitely many examples and everything is one of those, right? I mean, it's more like every subtree is unique, like snowflakes, but after a while, they're all blends of stuff you've seen before. They look like an average of two things you've seen before. They look like the offspring of two things you've seen before. And so when you have that kind of averaging process, then you can write down the coefficients of the averaging, and that gives you matrices. So I want to show you an interesting example of this kind of game, like a more geometric way to build a box like this. And it's going to show you a human foible that I've always found amusing. is people often project too much when they're thinking about math. They think that everything should be as well behaved as they'd like. Our job isn't to impose our will. Our job is to be a reporter, what we actually see. So let me go over here and write out this game. So the game is this. I'm not going to use the language of the complex numbers to describe this game. But if you know the complex numbers, you'll go, oh yeah, that's easy to describe in the complex numbers. The game is this, that I'm going to be in a circle. This circle, this disk is my universe. In other words, my state at any point in time is going to be a choice of a point somewhere in this disk. So this, just as in the original computer science example where you had x, y, z, w, your mood was captured by a finite choice. Is my mood x? Is my mood w? That's it. Well, here it's a more geometric situation. My mood is two-dimensional. Can you tell? You know, but it's definitely two-dimensional in an interesting way. It can be anywhere in this disk in 2 dimensions. Okay, and then now I want to launch. This is another way to build a machine inside this box. And again, I want to do this like the way you might find it in an Egyptian tomb, as opposed to using too much notation. But I actually think this way myself. I mean, I read accounts of Einstein or Thurston. They all encourage they encourage themselves to think like 3-year-olds. They think 3-year-olds are smarter than as you get older. And you just don't want to lose that. So the most important thing you do as K to 12 is to not suffocate the natural instincts and replace them with notation. That's always a mistake, right? But in any case, here's what I mean, is that I want to do yellow more of the time when I'm off to the left in this disk, and I want to do red more of the time when I'm off to the right in this disk. And I could just say yellow is a formula based on x minus 1 over, you know, I could write out equations for it. But the way I like to picture it in my mind, instead of writing equations for it, is that if I was carving something in a cave that represented this, this is what I would carve. I would carve this picture. In other words, the idea is that I look where my point is, and I drop down, and I look at how the line through my point cuts through this picture. And notice it cuts through mostly red and only a little bit of yellow. That means that most of the time I'm going to choose red, and only some of the time I'm going to choose yellow. It's like one way of saying it is I choose a random height in this where it intersects the bar and see what the color is. So in particular, if I'm all the way over to this edge, I have to output red. That's the only choice. And if I'm all the way over to this edge, I have to output yellow. And that's this choice. Okay? So, so now I need a starting position. Let's choose this as my starting position. And here's my machine. Decide to output red or yellow. I mean, we're building a box. The box has to flash a light the first time. Okay? And how do I decide? Using the rule. Using this rule that I drew for you, right? Okay, that's step 1. But now you notice that the common feature to all the drawings I did was that you have this hidden internal state, and you show the world something, and at the same time you advance your state. So as a board game, you would hop randomly from one board position to another board position. Here, I'm in this continuous realm. And in this continuous realm, what I want to do is shrink a little and rotate by phi, by angle phi if red, and angle theta if yellow. And they actually commissioned a study of Harvard undergraduates that you could get people to do worse in math just by using Greek letters. I thought it was fantastic. So this is the yellow angle, and this is the red angle. So if you know complex numbers, you just choose two random complex numbers whose magnitude is a little less than 1, and you multiply that by them. But what I'm thinking of here is, the red rotation rotates a little bit, and the yellow rotation is a different rotation a little bit. And each time I output a red or a yellow light, I also change states according to what the light was. But of course, this is all hidden inside the box. So you can't see inside the box to see what's going on. But if this is my starting position, and this is what it looks like, then if I output red, I could actually draw this. You could actually draw the whole tree. You could actually take this entire tree and draw it inside there. It would get really complicated after a while. But basically, if I do red, then my next state is here. If I do yellow, then my next state is here. But then I keep rotating like this. If I do red again, my next state is here. If I do yellow again, my next state is here. If I do yellow here, my next state is here. And what you end up getting is all the dots in this tree and all the points in this point cloud in infinite dimensional space. We get a point cloud here. And it doesn't take, you don't need to know the details of what the angles are to see that what's going on is that we're shrinking a little and rotating at random. And as long as the rotations are sufficiently general. If the rotation was always half turns, then this whole thing might end up a line. But if you choose nice random rotation values here, which I'd like you to do, then you end up getting an infinite point cloud, but most of the cloud is in the middle. And they're not that much out in the fringe. Okay? But what you can do is you can take this thing called, there's a notion of a convex hull, is if I have 3 points and I shrink wrap around those 3 points, I get this figure. If I have these 6 points and I shrink wrap around these 6 points, I get this figure. Just imagine putting plastic around it in a heat gun and so even if we have an infinite number of points, if almost all of them are towards the center, we can imagine shrink wrapping. We can imagine shrink wrapping, and there's an object which is a polygon, which it's not. So even though in principle I forgot this one. Even though in principle I said I'm inside the disk, for any actual example, if I look at all possible states are going to end up in a polygon. Okay, so here's an interesting geometric pun that I love in probability theory. In math, there are no coincidences, and everything you already know is just the tip of the iceberg of what you're going to see later, assuming you live long enough. I turned 61 recently, so I'm starting to realize the game does end, But basically, the tip of the iceberg here two uses. When you see two lists of positive numbers that add up to 1, or when you see a list of positive numbers that add up to 1, there are two possible meanings to that. Okay? So let's say 1/3, 1/6, 1/2. One possibility is that you can think of these as being probabilities. Okay? And so those are 3 numbers that add up to 1, and so it's a probability distribution, like red happens, green happens, blue happens. But the other way of looking at this is that these are the coefficients of a weighted average. Like if you have 3 numbers you want to average, then you could take 1/3 of the first number plus 1/6 of the second number and 1/2 of the third number, and that'd be like a weighted average of the 3 quantities. Like our electoral college. It doesn't one person, one vote. It gives heavier weights to some states than other states. Enough politics. Where this shows up geometrically is if you make a triangular region, then if you take in geometry the weighted average of the 3 corners, then depending on your weights, you could be anywhere between the 3 corners. So having 1 times this corner plus 0 times this corner plus 0 times this corner adds up to this point. And then 1 times this corner and 0 times the other corners adds up to this point. Having 1/2 of this corner and 1/2 of this corner and none of this corner is the midpoint in this line segment. And then if we wanted to instead take 1/3, 1/6, 1/2, then, well, I mean, this is halfway towards there, and this is 2/3 of the way. I mean, it would be this point. So the thing about these two views is that there are no rules in math that you have to stick to one view or the other view. You can treat them both as the same view. So in other words, if you were in a drawing like this that had 3 squares in the drawing, and you wanted to write down a probability distribution of what are the chances you're at x, what are the chances you're at y, what are the chances you're at z, you could state the 3 values. It's 1/3 chance I'm at x, 1/6 chance I'm at y, 1/2 chance I'm at z. Or you could draw a picture of x, y, and z and say you're here in the picture. That every point in the triangle can be thought of as a 3-way probability blend of the corners of the triangle. Instead of saying it's deterministic barycentric coordinates, you say probabilistic. It's just this represents that probability distribution of how likely I am to be in this corner versus this corner versus this corner. So when you use matrices to study these models, I mean, instead of having to think, well, I might be here or I might be here, you go, I am with certainty somewhere in between. In other words, you think of this as being material, and then if you're, let's say you're 2/3 of the chance, your chances are 2/3 you're here and 1/3 you're here. Or let's say after one step, if you start here, your chances are 1/3 you're here and 2/3 you're here. A more geometric way of writing that down is that your first step moves from here to here. If this is x, this is y, this is 2/3 towards y from x. This represents 2/3 of a chance you're at y and 1/3 of a chance you're at x. So people learn how to think in terms of this geometry when they're really thinking about probabilities. And so there's an interesting feature to this drawing. And the feature to this drawing is the following, which is that when people make this game, x, y, z, when they make games like this, they know that the output that's observed outside the box has to make sense as probabilities. So it's human nature to think that if I'm drawing a game like this, that the odds of moving along each edge should itself be a probability. Well, here's the biggest surprise in Schutzen-Berger's theorem, that you can come up with matrices for anything like this, is that when he comes up with matrices that produce actual probabilities for the outside world, the numbers inside the model don't necessarily stay between 0 and 1. The numbers inside the model don't look like probabilities. This is like mind-blowing. It's a really strange thing. And the reason I love this example is I can explain the difference here, which is that if I want to describe this point as a positive blend, I need, of these things, then I stay inside this region. But if I don't restrict myself to positive blends, then I get to leave this region. So let's say that instead of being 1/3, 1/2, 1/6, it was 1/2, let's say I had a -1/6. I mean, in other words, I could refer to a point outside the triangle by simply using numbers that are not positive. So here, if I chose the vertices of the hull are like drawing states on my machine. And if I just choose some of them, there are going to be points in this picture that are outside the triangle. And so they need negative coefficients in order to describe them in these drawings. So the only way to come up with a drawing which has all probabilities as edge labels is to take every single corner in the convex hull of this picture and use every single one of them and have that be a state in your picture. So it'd be very easy to come up with an example where there's a million of them. Whereas if you decided you didn't care, that it was just a preconception that was wrong, that the internal edges shouldn't be labeled by probabilities, then I could do the whole thing with a couple dimensions because the whole thing takes place in the disk. So that, when I first saw that, I thought it was pretty amazing. So that's it. Thank you. Are there any questions? I'm supposed to, you're going to be experimental subjects. You're going to be shocked and tortured. Oh, yes. So, okay, there are no questions, and people who are not in the class are free to leave. And I'm supposed to hand out an experimental subject.
I actually do have a question.
Oh, good.
So you started this by saying that using these drawings, you think we could take some of the math that is usually saved for college and bring it down into the K-12.
Yeah, yes.
Sitting here with my K-12 lens on.
Yes, yes. I got kind of away from that.
Yeah,
Okay,
a little bit.
Yeah.
But can you bring us back to it? Like, where do you see it fitting in?
Well, let me take, let's go up a dimension. Let's go up a dimension. There's this thing that, you know, every kid is aware of knots, and yet knots are studied in math in a different, in a higher level way. Is that when, you know, it's a classic knot problem. The way a mathematician ends up drawing a knot is they imagine they have a loop, a closed loop. Like if you were a climber, you carry loops like this, you can sling over things. Well, imagining a climber and pulling it out, like, how does it look like this? Didn't the manufacturer notice? You know, but this is a closed loop that's tangled in such a way that can't be untangled. Okay? But there are basic rules that people use for telling whether two drawings are actually the same drawing or not. And you know, one of the rules would be if you see a local region ignoring everything else. If you just zoom in on part of the picture, like outside the orange is not my concern. That if I see this, it's not actually caught on itself. And I could actually like pull it apart, right? And then a related picture is if I might actually zoom in and instead see a little twist like this. And I could pull that apart and turn it into this. And then the one that always throws people, but it's not so bad either, is you could have two lines like this, and then behind it you could have a third path like this. And that's exactly the same thing as two lines behind it. Let me draw the third path in a different color to make it more obvious. Imagine, you know, just as we could freely move these strings in our imagination, you know, we can freely move this back yellow string. So if we just move it over until it's over here, then you change this overlap pattern into this overlap pattern. So it turns out it's a theorem, these are called Reidemeister moves, that any two knots that are actually equivalent in the sense that you could play for an hour untangling them and get one to look like the other, you can actually untangle them just using these moves. So this is kind of like a visual notation. So, you know, I mean, I hope I have is, you know, deep learning, artificial intelligence, machine learning has been in the news a lot lately. It just beat one of the best Go players in the world, for example. But I'm fully, there's a podcast everybody who can should listen to, which is called Talking Machines. And you know, they have the wildest conversations on this podcast. There's like two seasons, 20, 30 episodes. They have the wildest conversations about different ways machine learning will be adapted in the future to us. But I'm waiting to pull out my cell phone, and it's had a year or two to get used to what I like best. And the interface has evolved. Like the primordial ooze has been evolving. So that now it's not the interface Apple shipped, it's the interface that works best for my preferences. It's gone with me as I make mistakes. Oh, he thinks he wants that over there, and it moves over automatically, right? So along the same lines, I would love to see iPads that had machine learning games that were evolved so that this was just one instance of thousands of possible games like this. In my experience, I mean, when I teach linear algebra, for example, I mean, people eventually get good at theory, but if you want, the best way to make people learn quickly is to find the thing they're brightest at and encourage that first, and then let everything else fill in afterwards. And I find if I want to make people feel smart, give them a really hard calculation they can actually do. So my sense of like what it's like in younger age groups is that people are extremely smart at visuals, and that if you were to come up with a series of games that were like mathematics but in a visual playing field, that that would accelerate people's interest in everything related to that. So I mean, to me, I mean, in some sense, when I was talking about the paths, yellow and red paths, I mean, this would unwind to a piece of string that was yellow then red. But string is one-dimensional. These pictures are two-dimensional. That's probably more interesting to people before they. I mean, in some sense, mathematicians learned to live cramped in these one-dimensional worlds who was studying math that was done on typewriters 20 years ago. But math deserves to be done visually in higher dimensions. Great. Thank you.